Hello everyone, I'm Mitali Sinha, a PhD student at IIIT Delhi under Professor Sujay. In this presentation, I'm going to talk about my PhD work on performance-aware design space optimization and attack mitigation for emerging heterogeneous architectures. In recent years, with the advancement of the application domain or the software domain, there is also a surge of high power and performance demand in the embedded system domain. To meet this need of high power and performance demand, the accelerator cores comes into the picture, which are hardware architectures which are custom designed to accelerate a particular functionality or a particular application. This results in an accelerator-rich heterogeneous SoC as shown in the figure, which is comprised of multiple and variety of accelerator cores, which is responsible for accelerating a given functionality or different kind of application, along with different general purpose cores and the memory systems all connected together by a network on chip. And all the system communicate with the off-chip DRAM. So as you can see here in the picture, each accelerator core has the accelerator logic, the data path in the controller, along with the network interface, which is responsible for communicating with different modules through the NOC. And it also contains a private memory for its accelerator specific data. In this work, we target two problems for such accelerator-rich heterogeneous SoC. The first is the shared resource utilization problem, and the second is the security threat for such SoCs. We propose different solutions, where the first solution is targeted for the shared resource utilization problem, where we propose a design space optimization framework. The other two solutions target the security attacks in such systems, that is the DOS attack detection and DOS attack localization framework. So in the design space optimization framework, we target the memory system to be the shared resource which we want to utilize efficiently given a particular heterogeneous SoC. The design optimization framework mainly comprises of two stages, the DSO stage and the DDA stage. That is the design space optimization stage and the dynamic data allocation stage. Before this primary two stages, we profile the accelerator memory access pattern. We profile the pattern in which the different accelerator communicate with each other and the general purpose cores along with the memory. So these access patterns are given as an input to the DSO stage. The DSO stage models the patterns or the access pattern of different accelerators. And we solve the analytical model using the MATLAB optimization toolbox. This DSO stage gives us an optimal private and shared memory configuration, and it takes an input as the area budget, which is the resource constraint in our DSO stage. Hence, the DSO stage provides a best memory configuration for a given set of accelerator-rich system. Under the resource constraint, here we consider the area budget as the resource constraint. This memory system configuration is then given as an input to the DDA stage, which performs the dynamic data allocation over the shared data distribution. By performing these stages, the proposed framework gives us an efficient memory configuration and data allocation. Our experimental results shows that with a baseline private-only memory system, we get an performance improvement with our framework of shared memory system as 25.42%. We get an energy efficiency of 23.48%, whereas we get an energy area savings for 43.77%. Our next solution is the DOS attack detection framework. To design an accelerator-rich heterogeneous SoC and to meet the time to market demand, the designers often bring the accelerator IPs from third-party vendors and then integrate together in a single chip. While this meets the time to market demand, as well as it also brings the optimized accelerator IPs from third-party vendors, however, it generates different security threats and vulnerability within the system. Since the accelerator IPs are brought from the third-party vendors, it is very difficult to verify or catch a hardware Trojan which may be present within the accelerator IP. As a result, the system becomes vulnerable and it can cause flooding attacks where a malicious IP can create a flooding attack by generating useless and frequent packets within the system. As a result, the system gets congested and the legitimate IPs are not able to communicate with each other. So to detect such kind of flooding attack, we propose our framework for DOS attack detection. The proposed framework is divided into two stages: low overhead sanity check and the ML-based attack detection. In the low overhead sanity check, it is responsible to generate an attack flag whenever it finds that there is something going on within the system and the timeout exceeds the accelerator execution time. So an attack flag is generated and then it triggers the ML-based attack detection stage, where all the feature statistics are collected from every node within the system, and it is passed to a cluster node which initiate the ML detection model. In this work, we collect efficient feature metrics, and we have a hierarchical trace collection strategy that also we have a hierarchical trace collection strategy, which is also responsible for the performance of the system. In our experimental evaluation, we get a detection accuracy of 97.40%, whereas a minimal traffic overhead of 0.57%. Our next solution is the DOS attack localization framework. Once an attack is detected within the system, it is very important to find out the attacker node or the malicious node within the system and then take appropriate actions against it. So our DOS attack localization framework targets to find out the malicious IP or localize the malicious IP within the system. Whenever an attack is detected within the system, our localization framework starts working. The localization framework needs a perceptron hardware to be implemented within the system for each node. Whenever a victim node within the system finds out that an attack is going on, it starts the localization process. It first checks with its neighbor connection or the neighbor links are under attack scenario or not. So to determine whether the neighboring links are in attack scenario, it uses the perceptron to find out whether the traffic is legitimate or an attack traffic. Whenever it finds that the particular link from where the attack traffic is coming, it generates a probing packet and it sends to the adjacent node. The adjacent node then starts the similar action and it finds whether its neighbor nodes or the neighbor links are under congestion or not. In the same way, it backtracks the path or traces back the path, the attack path, and finally reaches the malicious IP node. Our DOS attack localization framework gives an accuracy of detecting the malicious node as 98.35%, whereas there is a minimal hardware overhead of 3.30%, and along different network sizes, the accuracy is more than 97%. So in conclusion, we provide three solutions for the accelerated heterogeneous SOCs, where the first solution targets a design space optimization for memory subsystem, considering the interconnection latency and the resource constraints. Our second solution provided two-step flooding-based DOS attack detection framework using machine learning, whereas the DOS attack localization framework uses perceptrons at each router to accurately localize one or multiple malicious nodes. These are some references and publications of this work. Thank you.